sign in order to factor the polynomial. So then it's set equal to 0. Remember, factoring is not a good method unless it's set equal to 0. Only things being multiplied together that equal 0, you know they must equal to 0. If they multiply together and equal 5, you know nothing about them. Okay? So now I'm going to try to factor. What's the first thing I want to look for while I factor? Elijah? Good, a greatest common factor. And I'm really hoping there's a good one here because I basically want it to kind of narrow down to a quadratic so I can use all the factoring methods I knew from before. Okay? See? Good, so 3x squared is what we'll take out as our greatest common factor. That would leave x squared minus 4x plus 7. And then I would want to work on the x squared minus 4x plus 7. Is it factorable? No. Can I use quadratic formula or completing the square on that portion? Yes, because now that portion is a quadratic, so I have lots of options for that area, right? So just focusing on this part for a minute, we already know what's going to happen here. If we set 3x squared equal to 0, what are we going to get for x? 0. Okay. So that's 1, 0. What's the multiplicity of that 0? 2, because the x was actually squared. So if you factor that out, you'd have an x and another x, both creating the same solution of 0. But it would kind of happen twice. We wouldn't write it twice, but we want to acknowledge that here in case we had to graph it. So here, if I set this factor equal to 0, because it didn't factor further, like you guys said, my choices, completing the square, quadratic formula would work. What do you guys want to use? I don't care. Completing the square? Sure. It's not that bad, right? There's a 4 right here. Okay. So I'm just going to move the 7 to the other side. What's the amount that I would add to each side? 4. And for those of you that aren't sure, I took the middle term of 4, divided it by 2, and squared it, and that's how I got 4. So I would get x minus 2 squared equals negative 3. If I square root both sides, I get x minus 2 equals plus or minus I rad 3. So x is equal to 2 plus or minus I rad 3. Now, if they only asked me for the real solutions, I wouldn't need to find this. But all the directions here said is to solve. So if I'm unsure, I need to find all possible solutions. Okay? So how many solutions are there to this problem? So there's 3 unique solutions, but one of the solutions has a multiplicity of 2. Okay? How many times would this graph hit the x-axis? How many x-intercepts would it have? 1. Okay. What's the maximum amount of times a quartic could cross the x-axis? 4. Okay, because its degree is 4, it could have 4 solutions, 4 real solutions. Okay. But when we look at our solutions, though we have 3 distinct solutions and one has a multiplicity of 2, are we going to see these ones crossing the x-axis? No, they're imaginary, which means we're not going to see the function hit a real number on the x-axis for those solutions. Only for the 0, 1, doesn't say that. So if you were going to sketch this graph, let's look at this equation and say instead of equaling 0, it said equals y. Tell me what you know about this graph, just to kind of get in some review. We're done solving. We found all the solutions. Good for us. We did what the directions said. But I'm your teacher, right? And I have to make sure you can do more than just the directions and you can do all the other stuff. So a little bit of review. If this said y equals this, and I was trying to graph this, tell me what you know about the graph of this quartic function. Is he good? No? Just stretching? Damien? Good. End behavior is up and up. So evens end and start in the same direction, right? Because this is a positive leading coefficient, the end behavior would be up and up, right? How many times are we going to see it hit the x-axis? Maximum of 4, okay? However, these ones are imaginary, so it's not going to hit it those 2 times, which has narrowed it down to 2 times it could possibly hit. We only have one other solution, though, so it's only hitting one time at 0. How exactly is it hitting the x-axis at 0? What's that? Yeah, kind of like a parabola. So somehow it's going to come down to the x-axis, just touch it, okay, and then go back up. It might have some weird curves on the way because it's a quartic, but that's the general idea. Okay, so we want to start attaching pictures with functions kind of in our head, okay, knowing how they work. For this problem, though, these were the solutions. Okay. Yes? We'll learn that tomorrow. But what we are going to focus on in here is either doing it on the calculator if it's really complicated, or we'll always focus on giving you a 0 that you can at least start a process with to figure out the other one. Okay? So either it's going to factor and you can factor completely on your own, or if I tell you, hey, like 1's a 0, then you should be able to kind of divide. If you know 1 is a 0, then what must be a factor of the polynomial? X minus 1, right? And then you could like divide that out and then see what's left. And if what's left is factorable, you can get the rest of the factors. So that will kind of be our concentration tomorrow about division and how to do that and make sure we can get the rest of the factors. All right, so we're going to learn 2 new factoring patterns. Okay? So you guys know some special patterns. So we said when you factor, look for greatest common factor. Then after that, look for special patterns. So a couple of special patterns that you already should know, or a little bit of review if you don't know. So one pattern is the difference of squares. When you see 2 perfect squares that are being subtracted, there's kind of an automatic factoring pattern that you use for those. So if you see a squared minus b squared, how does that factor? If it said x squared minus 25, how would it factor? Yeah, so a plus b, a minus b. That's the way we get the perfect squares at the ends, right? Because these match, so that's how we get a squared. These match, that's how we get b squared. It has to be a minus, because otherwise the middle terms wouldn't cancel each other out, right? This makes a positive ab middle term. This makes a negative ab middle term, and they cancel each other out, which is why you don't see them when they're written here. Okay? Another is like the perfect square pattern that we talked about when we were completing the square. Like if the first term squared and the last term squared, and the middle term fits the pattern that you know it's supposed to be, then you know it factors as a perfect square. Okay? Since we're moving into higher powers, we're going to learn a cubed pattern. Because it's cubed and not squared, you do have a difference of cubes, just like you have a sum or difference of squares, but you can also have a sum of cubes. Okay? So here's the idea. If you see 2 terms that are perfect cubes, so they don't have any terms in between, it's just a beginning perfect cube and an ending perfect cube. What are some examples of perfect cubes? 8. What else? 27. 64. Okay. X cubed is a perfect cube. X to the 6th is actually a perfect cube too. Is that connecting in your head? What cubed makes x to the 6th? X squared, right? But if you cube it, you get, okay. Oh, yeah. 8x cubed is a perfect cube because what cubed makes 8x cubed? 2x. Okay. So there's a lot of, 1 is a perfect cube. Okay. There's a lot of perfect cubes. Kind of missed that one. Okay. All right, so there's a lot of perfect cubes, but again, because the way the cube pattern works, we can have both a sum and a difference. All right, so here's how they factor. Why they factor like this, we can look at if we multiply it back out, that it gets the middle terms to cancel. You might not like the pattern, but you got to learn it. Okay? So basically, the first factor is going to be small and just consist of the cube roots of these 2 things. Okay? So for example, I'll do a number example down here if you guys want. If this was x cubed plus 8, the first factor would consist of x and 2. I'll fill the signs in a minute. Okay? And these don't change for the sum or for the difference one. Okay? Now, the next factor is larger because this is a cube. So I need to make perfect cubes. If I just have another binomial, it will just be like this difference of squares. I would just be getting squared stuff all the time. Okay? So the next factor is actually a trinomial. Okay? The beginning and end makes sense, and it might be the middle that's a little bit kind of crazy. What would you have to multiply a by to get a cubed? A squared. So this starts with that. And at the end, what would you have to multiply b by to get b cubed? B squared. Okay. So it's kind of intuitive that those should be there. But it's the stuff in the middle that might get you stuck, and we'll look a little bit later about how that works when we multiply it out. So what I know here is that this would be x squared. This would be 4. The 4 is coming from 2 being squared. The middle term is the a and the b multiplied together. The reason that that works is because then when the a multiplies it, you get an a squared with a b. But you can also get an a squared with a b here in this multiplication that would cancel each other out. When the b multiplies that middle term, you'll get an ab squared. But you can get another ab squared right here that can cancel that one out. So the way it's set up is to make a bunch of middle terms that would eventually cancel each other out. Okay? So the signs become really important because if the signs aren't right, you won't get them to cancel out, right? You'll just end up with lots of terms in the middle. And then here, this middle term would be 2x. So here's the pattern that the signs follow. The last term is always positive, totally independent of the problem. So far the patterns look exactly the same, right? The only difference between the sum and difference formulas is going to be the signs that go here and here. Okay? The first factor matches the sign that you're factoring. So in this one, it's going to be an a plus b, and in this one, it's going to be an a minus b. The second one is the opposite of that because then that allows, once you've multiplied everything out, to get that ab squared and the other ab squared, one to be a plus and one to be a minus, and to cancel each other out. Okay? So here, when the first factor had a plus, this sign's going to be a minus, and when this one had a minus, this one's going to be plus. So these are the factoring patterns that we have to learn. Okay, so here, because this was a plus, this would be x plus 2, x squared minus 2x plus 4. Okay, you can see I'm going to make an x cubed. You can see I'm going to make an 8. And the stuff that would happen in between that, I'd get a positive 2x squared when I multiply these two together, but when I multiply these two together, I'm going to get a negative 2x squared. So that's going to let them nicely cancel out. When I multiply the x times 4, I'm going to get a positive 4x, but when I multiply the 2 times negative 2x, I'm going to get a negative 4x, and then those terms would cancel each other out. So you would just do a long distribution or FOIL process, and then all those middle terms would have different signs and cancel each other out. Okay? So if you like little things that help you remember patterns, Ms. Harper uses SOAP. So same, opposite, always positive. S-O-A-P. I'm not big on tricks, but same sign as what you're factoring, opposite sign of what you're factoring, always positive at the end. Okay? I don't know. You guys know I'm not a big trick person, but okay? Are we okay with this idea? Okay, so why it would become important for us to know this? Let's say we want to find all of the solutions, real or imaginary. Okay, big hint. On the test, I would probably just write solve or find the solutions. Okay, but here I'm trying to get across the point we're looking for both. Okay? Take a minute in your group and think about how you would solve this. Okay, so one option is how to start like this. Did anybody start this problem differently? Okay, so another option is to divide both sides by 2. So we can finish solving this one at this point, right? So x is equal to negative 3. How many solutions is that? 1. Okay? But it's a cubic, so it does have a chance at having 3. So there could be some imaginary solutions. So that's what's missing here. If we solve it the way we solved it in Algebra 1, we get the real solutions, but we don't have access to any complex solutions, okay? Which is where this method comes in, okay? So we are going to get this same solution over here in this method. If I go to factor this, what's the first thing I'm going to do? So I can take out a 2 or divide both sides by 2. So since it's actually set equal to 0, if we were just factoring and this wasn't here, we can't make the 2 disappear, right? It would still exist as a factor. Because it's set equal to 0, we can divide both sides by 2. We don't want to see that factor anymore. We can have this. And x cubed plus 27, how would we factor that?
X squared minus 6x plus 9.
3x plus 9. Here's the deal. This is not a perfect square right here. It's only a times b. It's not double a times b. So basically, once I factor with my cube pattern, is this ever going to be factorable right here? No. It's like almost a perfect square if this was double every time, but it's not, and so it's not factorable. So this is always giving you the imaginary solutions that exist with this one real solution over here. Okay? So then just like we saw at the beginning when we had a problem that factored, we can set each factor equal to 0. There's the same real solution we saw before. But if we're looking for all solutions, we really needed this other part here so we could finish solving. So let's say this time I decide to use quadratic formula. So negative b plus or minus b squared minus 4 times a times c all over 2a. Okay, so 9 minus 36 is negative 27. All right. 27 is 3 rad 3. And because it had a negative in the radical, I'm going to include the I. So those are my complex solutions that go with that. So obviously, if this question is asked on a test and you solve it the Algebra 1 way, you'll get a point for finding the real solution, but you won't get the other 2 points for the other 2 complex solutions. Does that make sense to everybody? Okay, so the factoring gives you an insight you didn't have before. You didn't see that in Algebra 1 because in Algebra 1, did you know complex or imaginary numbers existed? No. So this is an added element now that we're looking at this. Okay? All right, a little bit of calculator work. So if you have one, get one. If you don't have one, there's some in the back. Just drop your ID in, and we can use that. All right, so here's a graph of what's going on. I clearly need to be able to see more up here, okay, and maybe not as much to the right over here. So I'm going to go to my window. I'm going to change my x maximum to only like 7, but I need to change my y maximum to go up much higher. I'm just guessing right now, so I'm going to go ahead and try like 50. And then I'm going to press graph again and see if this was helpful or not. Okay, helpful, but I still don't quite see the top, so I'm going to go back again and maybe change it to like 70. And maybe I'll scale it by 10 since I've now made such a large graph. All right, so there's the cubic, okay? How many real roots does it have? 1. With what multiplicity? 1. See how the root goes straight through the graph? It doesn't act like a cubic right at the x-intercept. It doesn't hit it like a quadratic. If it goes straight through like that, that root just has degree 1 or multiplicity of 1, which means it is a cubic. It could have up to 3 roots. We only see 1 real one, so how many imaginary roots would exist? 2. Okay? So if you were factoring to solve this, there would be one real root with two imaginary roots. We're not going to factor to solve it. What I want you guys to see is, can you find the zero, the maximum, and the minimum on your calculator? So all of these things you should know how to do. We did this with quadratics. You saw in the notes last night how to find the maximums and the minimums, correct? Okay, and we had done that with quadratics also. So just a little reminder, can you go to second calculate? Can you find a maximum, which would be this point up there? A minimum would be this point right there, and the zero would be where it's crossing right there. Okay? Are the maximum and the minimum here absolute maximums and minimums, or relative maximums and minimums? Relative, okay? This function has no maximum and minimum, like absolutely. One other note, an odd degree function, does it have to cross the x-axis? A function that has odd degree, will it always have at least one real zero? Yes, right? Because it goes up one way and down the other, so eventually it's going to have to cross the x-axis at least one time. Even degreed function, do they have to cross the x-axis? No. Just like quadratics, they could completely exist above or below. So just something to keep in mind so that you have a better understanding of how the functions work. So just go ahead, find the max, the min, and the zero. Check with your group that they found the same numbers, okay, and that you're able to find that. Okay. So a zero is a solution. So when you list it, you can list it as x equals, because you're giving me an x value that makes the equation equal to 0. And what was the 0? Negative 4.7. Okay. For the relative maximum and relative minimum, those are points on the graph unless they ask you for the value or where it occurs or something more specific within the point. So what was our relative maximum? Somebody raise your hand and list it for me. What was the x coordinate?
Negative 2.83.
Okay, and then what was the y coordinate with it, Matt?
I think 54.
Oh, sorry, just Lane, I told you. Is this okay with everybody?
Yeah.
Is that approximately what you got? Okay. What about for the relative minimum? Can somebody different raise your hand and give me the minimum point? Yeah, Denisa?
I got 0.83 and then 5.
Look good? Comparatively to what you have? Okay. So that's not anything new. It's just an old thing we've already done, but with a new shape that's sitting on the graph. Okay? So tonight's homework is homework 3.